Okay. If you don't like the jumper, you might want to leave now. It's a health and safety warning. It's about to follow you for some more T-Rex for the next 30 minutes. I'm going to talk to you today about some research I've been involved in over the past 10 years almost, where as a team we are trying to reconstruct soft tissues in a range of groups, including dinosaurs, in order to build biomechanical models that will tell us something about the way these extinct animals move. The reason that we do this is because assessments of biomechanics and function are key to understanding many of the most important transitions in the history of life. Because these transitions inherently involve new functional behaviours that allow animal groups to diversify into new ecological niches. Some obvious examples: colonisation of the land by the earliest tetrapods, the evolution of flight, our flight in birds, and within our own lineage, the pinnacle of all evolution, bipedal gait in humans. As well as helping us understand major transitions and the history of life, extending biomechanical analyses into the fossil record also allows us to ask questions about how organisms work that we can't ask by looking at living animals alone. And dinosaurs are a great example of this, as they have many unique features that we just don't see in extant groups. They allow us to look at postural transitions, in particular the switch from bipedal postures to quadrupedal postures, which actually occurred on 3 independent occasions within ornithischian dinosaurs. Perhaps most obviously of all, something I'm going to come back to later in the talk, is locomotion at extremely large multi-ton body sizes. We can also look at convergent evolution and the repeated evolution of specific traits that may be functionally important. And of course, a very hot topic, the evolution of avian locomotion, the evolution of powered flight. And the importance of biomechanical analyses of fossils is nicely summed up, I think, in Whitmer's famous pyramid of inference, where we can see what Whitmer was trying to conceptualize here is the process that we go through as scientists, where we start with our raw fossilized data and we increasingly build up a picture about the biology of extinct organisms and put that together to say something about community structure and evolution. And you can see that sandwiched right in the middle of this tier is functional morphology, linking our anatomical reconstructions to our big picture inferences about the history of life. And what Whitmer highlights in particular in his paper is that all these big picture interpretations and our interpretations of functional morphology are built on either explicit or implicit assumptions about soft tissues that are regularly not preserved in fossils. Now, by explicit, we mean a process where the biomechanical assessment, the functional assessment, includes an actual reconstruction of the soft tissue. By implicit, we mean that we've skipped out that stage and we're basing our functional reconstruction solely on the bones. So essentially what we're doing is assuming that either the soft tissues don't matter, or if we're comparing two groups, all things are equal in the soft tissues. And this is the more traditional approach that paleontologists would take, is to base their functional inferences on bones. So typically we'd see things like limb proportions being measured and then plotted onto morphospace diagrams to see where our extinct groups plot relative to extant groups, and that might tell us how our extinct group moved relative to the way that extant animals move. Or quite commonly we look for morphological hallmarks diagnostic of certain types of locomotion, and the classic one are so-called cursorial morphological features that indicate competent running ability. A really classic example of comparative skeletal anatomy and diagnostic function in extant taxa, in fact, one of the best examples comes from our own feet and our own lineage. So a real classical morphological hallmark of upright, competent bipedalism in humans is the structure of our foot and the possession of arches in our midfoot, which of course all non-human apes lack. flat, flexible feet and no arch in their midfoot. And that translates to diagnostic features in the way that we move. So this graph shows the vertical ground reaction force. The dotted line is a human during walking, and you see this two-humped profile that represents the way in which the arch absorbs the impact of heel strike and allows us to vault over and propel our centre of mass forward. And this is a very energetically efficient way of moving that non-human apes just aren't capable of doing. So if you're out in the desert in Africa and you find a fossil foot bone from a hominid, you measure its shape. If it comes out more human-like than non-human ape-like, you quickly search the formatting guidelines for nature because that means it has a stabilised midfoot arch and your fossil is a competent terrestrial biped. The issue, of course, is that quite often these functional paradigms are not based on an enormous amount of data from living animals, because these things are inherently difficult to measure. So with the example of a human foot, if we want to actually measure how the arch of a human foot moves, then the only way we can do that directly is to either surgically drill pins into the bones of the midfoot and measure how those pins move, or to expose people to ionizing radiation to observe how those bones move directly. Of course, surprisingly, there are not many volunteers for these experiments, as you can imagine. So, if you've ever suffered from fallen arches or flat feet, you may be familiar with this kind of data. Instead of measuring bone motion directly in the midfoot, what we typically do is to look at the pressure that the foot exerts on the ground. This is often how flat feet are diagnosed. So, oops, that's jumped the wrong way. What you would typically, in an evolutionary context, would look at these pressure records where the red areas are areas of high pressure. And what you would expect for a stereotypical human is to be at this end, where there is very little pressure in the midfoot, which indicates that the arch is stable, it's not in contact with the ground. But actually, when we collect lots of data from lots of individuals and lots of footsteps from individuals, so we get a variation step to step, what we see is a huge spectrum where, yes, an awful lot of people are very stereotypically human-like, but we also have a lot of individuals where their pressure records resemble those of chimpanzees and bonobos. So we have a problem here with skeletal diagnostics, because human-like foot bones and human structure are producing non-human ape-like functions. It actually gets even worse when we start to look at step-to-step variation within individuals. So what this graph shows is for each of these numbers is pressure records, about 500 pressure records from individual human beings. And the white bars show footsteps that look like this, very human-like. The grey bars show intermediate steps where the midfoot pressure is moderately high. And then these black bars are steps where the midfoot pressure is very high. And what you can see is that, yes, a lot of human beings are stereotypically human. But we also have a lot of human beings where the midfoot pressure is changing every step. Some steps they walk as you'd expect a human to walk, and in other steps they're leaving chimpanzee-like pressure records. Their midfoot is not stabilised. So in terms of the comparative approach and how we diagnose function in fossils, this is a problem because bone morphology is not changing these individuals step to step, but function is changing. So soft tissues are determining function. Coming back to dinosaurs, what are these kind of examples are becoming more complex as we collect more data on living animals. So what does this mean for dinosaurs, which are actually weirder animals than hominids? When we make functional inferences from skeletal tissues in dinosaurs, should we expect greater error? And how do we move past this uncertainty and this ambiguity in skeletal evidence? So what I'm going to do for the rest of the talk is kind of use a case study example of how we might incorporate soft tissues into our functional assessments. And I picked probably the most important question in all of science: was T-Rex a fast runner? The reason this is actually genuinely an interesting question is that locomotor biologists are very interested in skin. Body size has a huge effect on the way animals move. maximum performance in locomotion is also crucial to ecology. And those two things put together are particularly interesting in terms of T-Rex, because there's been an awful lot of speculation about how T-Rex may have moved from the capable of. And in particular, some very long-standing speculative ideas that T-Rex may have been able to cheat scaling rules that we see in extinct animals, and this may have been crucial to the way it interacted with its prey. So if you go back in the literature, you see commonplace statements like this, that T-Rex had exceptional locomotor ability. And yes, a lot of these ideas are quite old and rely on quite qualitative evidence, but actually even recent analyses have kind of supported these ideas to some extent as well, with this recent paper claiming enhanced balance, cursoriality and turning agility in T-Rex. So why do you think this? Oops, skipped it again. The reason they think this is because T-Rex looks quite fast. If you measure its limb proportions, it comes out among extinct animals in this subcursorial group where the limb proportions of the equivalent living animals would indicate reasonable locomotor ability. Similarly, if we look at our hallmarks for locomotion, T-Rex comes fairly high up on the scale. It has quite long, gracile, distal limb segments that we see quite commonly in extant animals that can run quite fast. The problem with that is that it flies in the face of what we know about scaling in living animals. So as body size increases in living mammals, what we see is that muscle mass scales asymmetrically with body mass. But unfortunately, muscle force is determined by cross-sectional area, which scales negatively. So although the muscle volume is keeping up with body mass, the actual area, the force-producing component, is scaling negatively. Similarly, as muscles get longer, contraction speed decreases, and these same geometrical scaling rules are also occurring in the bones as well. So the bones can't keep up with the stress either. And as a result of that, once you go above something about the size of a horse, locomotor ability starts to decrease in living mammals to the point where in elephants, they are no longer capable of true running. In order to get past this kind of juxtaposing view, we need a way to reconstruct maximum locomotor ability in a fossil. And the way we think about this is to go back to basics, and back to Newton. If we want to know something about the motion, we need to know something about the force and the mass that's inherent in an animal. So to get there, we need to characterize the skeletal geometry, because that's telling us the distances between the joints and how the joints can move. We need to know something about the muscles that are generating the force. And we need to know something about the mass properties of the animal, how much each of these body segments weighed, and how that mass was distributed within the body segment. The problem, of course, is that in a fossil, we don't have the muscles, or we don't have the body volume or the body shape. So how do we do it? Well, I'm going to go through it, starting with the mass properties. There are lots of methods for estimating the body mass of fossils. I'm going to talk exclusively about volumetric approaches, digital volumetric approaches, because in general these are considered the best way of getting to body shape as well as body mass. And also Roger's stuff like that. I say bad things about scaling approaches. So this is how we would typically create a volumetric model of a dinosaur. We would use some sort of method to digitize the skeleton in 3 dimensions, photogrammetry or laser scanning, and then we would use computer-aided design to sculpt a volume around the skeleton. We have volume, we can design density, and we get a mass. And the computer will also tell us where the center of the mass is at the same time. There are many logistical advantages to this approach. The main problem, of course, is that it's totally subjective. I can make this Allosaurus as skinny or as fat as I want to. Very subjective. So what we typically do as honourable scientists is we acknowledge this uncertainty and we create a range of different reconstructions from very skinny to very plump, and that gives us a range of values for body mass and a range of centre of mass predictions as well. So although we're being quite rigorous in acknowledging our subjectivity, the uncertainty in the error bars become quite large. What we've been trying to do is come up with a more objective method to do this. So what we decided would be useful is if we could come up with a measure of how large the body volume was relative to the skeletal volume of living animals. And then what we could do is come up with a way of predicting how large our soft tissue should be in the skeletons of fossils. So what we do is we digitize our living animal skeleton and we produce a shrink-wrapped volume around that skeleton in a mathematical algorithm. So it's totally objective. Whoever presses the button gets the same answer. And it's giving us a crude estimate of the volume of the skeleton alone. We can then segment out the skin volume and look at the ratio between this shrink-wrapped volume and the skin volume. And it tells us how much we have to expand that shrink-wrapped volume by to get a true body volume. What we've been doing recently is doing this for a range of birds and crocodilians and lizards, so that we can come up with scaling exponents for each of these body segments that we can then apply to a dinosaur to get a empirically generated body volume for a dinosaur. And this is our reconstruction of T-Rex. The important thing to note here, contrary to all Jacob's work, is that dinosaurs were bright green. And so here's our T-Rex reconstruction, stand the T-Rex from the Manchester Museum, and we come out with a value of body mass of 7,200 kilograms for this particular T-Rex. And it's broadly similar to the estimates that the more subjective volumetric approaches came out with, and it's a lot higher than the body masses that were used in some of these earlier papers that claim very high athletic ability for T-Rex. And this is possibly why some of the arguments for athletic T-Rexes were coming out, because they were coming out as more footed animals. So we've looked at body mass, we've got our properties of mass, the centre of mass, etc. We then need to look at the muscles. And this is something that paleontologists have been doing very well for a long time, reconstructing muscle origin and insertion points for muscles in dinosaurs based on the extant phylogenetic bracket approach. So basically we look at the skeletal correlates for muscle attachments in crocodilians and birds, and then try and reconcile that with the muscle scans we see on fossil bones, and we can get a pretty good idea of where muscles go to and from in these animals. More recently, we've been taking this a step further by actually mapping on three-dimensional muscle paths onto digital models of fossil bones. And this gives us values for the moment arms or the leverage of these muscles. And what that allows us to do is to begin to start assessing these claims of very high locomotor ability in animals like T-Rex. So one way in which people have speculated that T-Rex can achieve these scaling rules and run very fast is by having very high leverage in their limb muscles. Unfortunately, when we look at the data, large multi-ton, 6-ton plus theropod dinosaurs don't seem to have any greater leverage capacity in their muscles than small and medium-sized theropods. So there's no evidence that these animals were able to increase their locomotor performance by having very large motor arms. The next stage, once we have the muscle paths in place, is obviously to come up with some values for the size of these muscles. The bigger the muscle, the bigger the force. So we need a value for muscle mass. Unfortunately, this area hasn't been as well investigated as it could be. I'm hoping we can change that with a PhD we're advertising at the moment. Typically what people have done is to basically scale values from living animals, which is quite crude. The only muscle that's really received serious attention is the large cornifemoralis muscle, and And using this approach that we've used in various papers where we sculpt this muscle in 3D, we can come up with a value for the cauda femoralis muscle. We validated this in alligators and we can predict the cauda femoralis size in an alligator to within 5%, so that's quite promising. But again, when we look at theropods, there's absolutely no evidence that this muscle is getting relatively bigger than large theropods in the way that we would need to support higher locomotor ability as these animals got bigger. Unfortunately, although this is all very nice, with numbers and reasoned arguments that large theropod dinosaurs like T-Rex could not cheat these scaling rules, we're not really any closer to an actual quantitative estimate of how fast T-Rex could grow and what it's really capable of. How do we take that next step? Well, we're actually nearly all the way there. We have most of what we need to solve this equation. We've done the mass, we've done the force. If we put that together into a musculoskeletal model, and then use physics simulation, it should be theoretically possible to solve that equation and come up with a prediction of maximum performance. But the problem is, we're missing something. We don't know when and what forces to apply. What we need is a way of coming up with a coordinated activation pattern for those muscles, a way of applying the force in the best way to generate maximum performance in that animal. To do this, we essentially use a genetic algorithm approach, so it's a machine learning approach, and basically through trial and error, we search through the millions of different options for muscle activation. Inevitably, what happens when we start is we find very poor solutions, because there are billions of possible solutions, the vast majority of them are rubbish. But with using a very big computer to search through all these options, we can eventually move towards something that's very sensible. And if we continue to optimize, search through all the different possible combinations, we can eventually get to something that looks convincing as an optimal breeding for that particular input morphology that we've specified. Now, this looks very pretty, but the obvious question is it a valid approach? And in the past 15 years, Bill Sellers has gone to great lengths to demonstrate that it is. So he's done lots of reconstructions of human walking and running, various analyses of chimpanzees. Believe it or not, this is an ostrich. And in general, for very specific parameters, these models work really well. They predict things like stride length and metabolic cost in human walking to within about 10%. And our predictions for maximum running speed in ratites and humans are pretty close to published values for those animals. But again, that's not enough on its own, because for these running animals, we have all the input data. We know exactly how much mass a human being has in his legs, we can measure it. With dinosaurs, we can never be that certain. We've always got error bars. And when we acknowledge those error bars in these simulations, when we rerun these simulations and vary parameters for muscle physiology and body mass and fiber length, across the range of certainties that we have for these parameters, we get error in speed predictions. Now, these error bars are not so large that they include very fast speeds, like the ones I was quoting at the start. So we can rule out those very fast speeds, but nevertheless, these error bars are still huge, and they are much bigger than we would like to be able to do the macroevolutionary analysis of running speed or walking energetics in extinct animals like dinosaurs. So the question is, how do we do better? Well, what we decided is that we need to go back to the models. We need to maximize the fossil evidence that we have. And there's really classic work done in the late 80s and 90s by Beamer that showed that the stress in limb bones of living mammals and birds is essentially constant with body size when these animals are carrying out maximal activities like running and jumping. So essentially, we have the failure stress of bone in this zone here, and across this range of body size, the actual maximum stress that these limb bones are experiencing in fast running and jumping is within this fairly constrained band. So basically these animals are maintaining a safety factor of about 2 to 4 relative to the failure stress of their bones. Now our existing simulations of dinosaur running do not include bone stress, we just ignore it. But we do have the cross-sectional areas of long bones of dinosaurs fossilized. So what we asked ourselves was that if we include bone loading in the simulations, will it restrict the range of prediction that we get for extinct animals like T-Rex? So that's exactly what we did. So rather than asking the model to just run as fast as it can in 5 seconds, ignoring bone stress, we included bone stress in the optimization criteria. So initially we were very generous and allowed very unrealistic stresses, and we gradually limited that stress, and you can see what it did was to reduce maximum running speed. So if I put our failure strength on there, and then the safety factor range that we see in living animals, when we allow the model to break its bones and do what it wants, bone stress is not really having any effect. Running speed's going up and down each day, but it doesn't really care, it's not important. When we start, and as a result of that, the T-Rex achieves true running gains. It's got an aerial effect, it's genuinely running. When we start to limit bone stress to realistic ranges, it's starting to change the way the model behaves. It's having a determinant effect on running speed. To the point where, when we get into realistic values below about 150 megapascals, the model is no longer running. It can't maintain an aerial effect where it has to support all of its body weight on one limb. So basically, we've reduced the range of plausible maximum speeds, and we've ruled out true running gains in T-Rex. I couldn't catch the gene. We are still waiting to hear from the Nobel Prize Committee. You never know. So, to sum up, I'm not rubbishing traditional comparative approaches at all. They are a fundamental tool in every way. But I think that by incorporating soft tissues with hard tissue evidence and building these biomechanical models, we can provide a bit of a firmer base to climb Whitmer's pyramid and say important things about these animals. One final plug. We're looking to do more work in this area. We're offering a PhD at Liverpool, concentrating on muscles and reconstructing muscles in dinosaurs. If you have students, or if you are a student, if you're interested, please contact me. And I'll just finish by acknowledging all these people that were involved in this research and the symposium.